We're going to continue on here. Not sure if that projector is going to pick anything up, but at least one out of two is not bad, I suppose. We've been talking about at the end there, really intermolecular forces, and intermolecular forces are, as we talked about, really the sort of bonds that hold one molecule together with another. And all intermolecular forces are really a basic combination of sort of positive and negative attraction between the different molecules as to what holds that guy together. And we talked about some different types. We talked about dipole-dipole interaction. That is really the interaction that occurs between really polar and polar molecules, which lack the ability to hydrogen bond. So a positive side of one is attracted to the negative side of the other. And again, that is where that interaction basically occurs between them. A special type of dipole-dipole interaction is what is known as hydrogen bonding. And in order for hydrogen bonding to occur, you need a bond between hydrogen and one of those kind of electronegative atoms, and nitrogen, oxygen, and fluorine. And as we talked about, if they are those guys there, they will definitely be very polar, that bond. And that is like kind of what we see when we have something like water here interacting with itself or others. It is able to basically do so through, again, really the opposite of signs there. The negative oxygen attracted to the positive hydrogen in that particular case, and that's hydrogen bonding. It is really the way polar molecules and polar molecules interact that obviously have the ability to hydrogen bond. So remember, not all polar molecules have the ability to hydrogen bond. They do need that hydrogen attached to a nitrogen, oxygen, or fluorine. Lastly, we talked about dispersion forces, which are really the weakest out of all of them. These are weak temporary type forces. And this is really the main force for how nonpolar molecules interact with other nonpolar molecules. And we talked about really a couple of ways that, they could kind of do this interaction. One way, as I mentioned, is sort of what is sometimes referred to as an induced dipole, where something with a charge comes next to something that is nonpolar. It creates really a shift in the electrons in that nonpolar molecule, and it temporarily sort of gains a positive negative side, and it's able to then interact obviously with a, say, polar molecule for a short period of time until the kind of electrons move back. The other way is just sort of naturally nonpolar molecules and the other nonpolar molecules, their electrons will just kind of all end up in one side of that molecule versus the other. And again, temporarily create this positive and negative attraction. So normally where there is no sort of separation of charge, because of those electrons kind of moving around, they temporarily do gain a charge where, again, they can sort of interact with each other. These are temporary, as I mentioned, because, again, as the electrons go back, then they're going to kind of move around and make new interactions. And that's different than any type of polar molecule, because a polar molecule has a dipole moment. It has basically a fixed, always, no matter what the situation is, a side that's positive, a side that's negative, which means it's good to go with these interactions out of the box, if you will. It doesn't need anything to happen for it to be able to interact. And that's really the main difference there between dipole-dipole hydrogen bonding and dispersion. In terms of the strength of them, the strongest interaction is the hydrogen bonding. Followed really by the dipole-dipole, and then the dispersion would be the weakest interaction out of all of them. As we talked about, these type of things affect boiling points and melting points. So the stronger the attraction, so if you have something that can hydrogen bond, it's going to have a much higher boiling point than something that is using dispersion forces. Is going to have a much lower boiling point because of the weak interaction that occurs. It also, as we touched upon as well last time, affect things like solubility, how things sort of mix together. So if you find things that work with very similar intermolecular forces as they do with themselves, it typically will make them kind of soluble in each other as well. In terms of dispersion forces, again, they're the weakest, but the strength of a dispersion force, so if you're really kind of comparing something like which one would have a higher boiling point with two sort of nonpolar molecules, the strength of dispersion forces does increase with molar mass, because with more molar mass, more atoms, more electrons, greater chance for the electrons to kind of move around and get those kind of dispersion forces basically occurring. Any questions on any of that stuff there? So I think we finished up on this slide. So here's just some pictures of this, these interactions. Again, these intermolecular forces, as we also talked about, are definitely always weaker than any intramolecular force. So once again, an intramolecular force is a force within the molecule. So that's like your ionic bonding, which is super strong, and like your covalent bonding where they share electrons, also stronger than any intermolecular force that occurs. In the solid, what ends up happening is these guys, no matter what the situation is, there will sort of be a negative guy near a negative guy and a positive side near a positive side. But what they continue to do is really sort of move around and kind of adjust their positions so that they can maximize areas where they come into like a solid or a liquid, where they could kind of get those positive sides near negative sides. So there'll be a lot more attractive forces than repulsion forces. But again, no matter what you do, there's going to be some positive near each other and negative near each other. This is water, which is polar, and obviously again our oxygen being more negative, hydrogen being more positive, giving us those hydrogen bonding that occurs here. And again, the hydrogen bonding, because that hydrogen, for example, is bonded to a oxygen over there. Here's sort of the idea of an instantaneous dipole. And again, our guy on the left there just sort of gains a charge. And it's going to cause this guy that normally does not have a charge to also temporarily gain a charge. And once again, that's going to give a positive side of one molecule, a negative side of another, and they're going to temporarily be able to interact with each other. Pretty much everybody could do some type of dispersion forces. That's why when you mix something like, say, oil and vinegar salad dressing or something like that, it stays mixed for a bit, right? But after a while, everybody kind of separates out from each other. And again, for a short period of time, you know, everybody can kind of interact with each other through dispersion forces, but they can't really maintain those interactions, especially if you got somebody that wants to use hydrogen bonding and somebody wants to use dispersion forces. Really, the only ones that kind of can maintain that over a long period of time are other nonpolar molecules where they're doing the same thing, kind of breaking apart and stuff like that. Any questions on intermolecular forces? Yeah. Next, we're going to talk about specific heat. Specific heat, there is an equation that goes with specific heat, which is Q is equal to ms delta T. This is the heat that is there, and that's usually in 2 units, either 1 unit. Joules are calories. M is mass, which is in grams. Delta T is the change in temperature, which should always be the final temperature minus the initial temperature, and is one of the few things in chemistry where we actually keep it in degrees Celsius. We actually don't convert it to Kelvin in this case. And that is because S, I personally use S. Some people use SH, some people use C for this, and that is the specific heat capacity. And the definition of specific heat capacity is up here. It is the amount of energy required to change 1 gram of a substance by 1 degree Celsius. So it typically has 3 units associated with it. Joules per gram per degree Celsius are calories per gram per degree Celsius. And that's also why we keep the temperature here in Celsius, so everything cancels out correctly. The specific heat of liquid water, for example, 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius is the specific heat capacity of liquid water. There's a conversion I think we talked, maybe when we talk about energy, that's also pretty useful here, and that is 1 calorie is 4.184 joules. So that's a conversion that's sometimes used here. That is why specific heat of water is what we see here, 4.184 and 1 calorie per gram degree Celsius. We use the specific heat capacity to really figure out how much heat is either absorbed or released in a process where we are changing the temperature of a substance, but that substance remains in the same phase. So we have something like liquid water, which is liquid all the way through the temperature change. We can figure out how much energy the water gained. We can figure out how much energy the water gave off. So that is what we use specific heat capacity. The larger the specific heat capacity, do you have to put more energy in to change the temperature or less energy? You need to put more energy in if you have a larger specific heat capacity. That's why something like water, which has a relatively high specific heat capacity of 4.184 joules per gram per degree Celsius, you got to throw in there 4.184 joules for every gram of water you want to change by 1 degree Celsius, which is why it takes an enormous amount of energy to change the water temperature of the ocean by a very small amount, which is why people go, hey, it changed by like point something degrees, and people go, well, you know, it's only point something degrees, but it takes a lot of energy to change the temperature of the water by that small amount of temperature. Here's a list of specific heat capacity, and you know, if you do have to go to a table, you do want to make sure that especially a table like this, which looks like it's from your book, it has both units there, calories per gram per degree Celsius or joules per gram per degree Celsius. You want to make sure that you find the substances you're looking for, and you also want to make sure that you do find it in the correct state. So water is a very common one. Where you're doing liquid water, it is the 4.184 number. But if you're doing something like ice, which is also water, it would be more like 2. If you're doing something like steam, which is also the gas version of water, it would also be something like 2 as well. So you do definitely, as you can see down here, these guys are much different than liquid water, and they're all basically H2O. So you want to make sure that you do get the correct phase. So let's take a look at one. How many calories? We'll do calories that are needed to heat a pot of water, 1,600 grams of it, from 25 degrees Celsius to 100 degrees Celsius. So we can use our specific heat equation. Now we have our mass, which is given to us in this case, which is 1,600 grams. We have our specific heat capacity, which we could find for that off that table. Joules and calories. I'll just use the joule version there first. 4.184 joules per gram Celsius. Or if you want to, 1 calorie per gram per degree Celsius. The initial temperature here is 25 degrees Celsius. Our final temperature is 100 degrees Celsius. So if we put this into our equation, Q would equal our 1,600 grams. We'll use 4.184 joules. And again, here we do want to do final minus initial temperature. So my final temperature is 100 degrees Celsius. My initial is 25 degrees Celsius. And if I do all that good stuff there, 1,600 times a 4.184 times basically a 75, I believe, going to give me, I believe this is 502080. This calculator is hard to see. I think that looks like a comma there. The units, by the way, would be here if we cancel all this out. It would be joules. So if we wanted to do a little significant figure action here, that's like a 75, which is 2, which means we really could do something like 5.0 times 10 to the 1, 2, 3, 4, 5 joules in this case. Any questions on that one there? Now, we could just use the conversion factor at this point and convert it to calories, or we could go into the equation, obviously, with calories, and, you know, whichever way you want to do it. So you could do, again, 1,600 grams. You could use the 1 calorie per gram per degree Celsius. And once again, our 100 minus 25 degrees Celsius. And if we do that, which is obviously the same thing you would get if you use the conversion down there. Looks like 1.2 times 10 to the 5th joules in that calories in that case. And again, that should be pretty much what you get if you divide the bottom one by 4.184, basically. Question on either one of those. And like I said, at that point, you could do this. And should get you up there. Now, when we look at the specific heat equation, there's only really one part of that that can get you to a negative number. And by the way, when we do calculate a Q like this, that is a positive number. Is this exothermic or endothermic? This would be a endothermic process as Q is positive. So remember, anything involving energy, kind of a positive value there, it's going to be endothermic. Exothermic would be a negative value here of Q. So endothermic means it's absorbing energy, and that's basically what we see here. When the water absorbs the energy, the temperature goes from 25 to 100 degrees, right? Temperature increases as a result of it absorbing energy. The only thing that would get us a negative value or an exothermic one would be if our final temperature was lower than our initial temperature. That would give us a delta T that would be negative, and that would give us an exothermic process, which is what we would expect. If somebody released energy, it would be giving off energy, right? And their temperature would come down as a result of that. And your final temperature would be obviously less than your initial temperature. Any questions on that one there? All right, so why don't you try one here? Let me just write one up here. Let's go with 294 joules of heat is transferred to 10 grams of silver at 25 degrees Celsius. What is the final temperature in degrees Celsius of silver? The specific heat capacity of silver is 0.24 joules per gram per degree Celsius. All right, so take a couple minutes, see what you come up with. We're looking for a final temperature in this particular. Okay, let's take a look at this. So obviously we are dealing with specific heat. So our Q equals ms delta T. We do have our Q given to us in this case, which is the 294 joules. We obviously have the mass, which is the 10 grams. We have our initial temperature, which is 25 degrees Celsius. We are looking for our final temperature. And in this case, they gave us the specific heat capacity of silver at 0.24 joules per gram per degree Celsius. So really, we got Q, we got M, we got S. We can just rearrange and solve for delta T here to start with. So delta T would equal dividing basically these two guys to the other side. Would give us Q divided by MS. In this case, putting in our numbers would give us 294 joules divided by our 10 grams and our 0.24 joules per gram per degree Celsius. And obviously joules here will cancel, grams will cancel, will leave us degrees Celsius, which is good since that is a temperature. And that's a 294 divided by 10 and divided by 0.24. It gets us like a 122.5 degrees Celsius, which would be our change in temperature. If we wanted to sig fig it out, it looks like 2 would be it based off of probably that number right there. So we can take it to like a 120 degrees Celsius. That once again is not the final temperature, but that is actually the change in temperature. And that's why the understanding that the change in temperature is the final temperature minus the initial temperature. So using that equation, we just figured the change in temperature and we had the initial, so we could rearrange it, and the final temperature here would actually be the change in temperature plus the initial temperature. That would give us a $1.20 there plus a 25, about a 145 degrees Celsius would be our final temperature here. Any questions on that there? Yeah. Are we talking up here or on this part or? Yeah. Yeah, I mean, you probably should in this case. I'll be honest with you. Personally, I probably would just keep going with their whole number there, 122.5. But probably the right thing to do would be at that point to probably round it to the right sig figs and then add the final number there. Yeah. Since technically it'd be kind of like 2 different operations. You're kind of multiplying, dividing, then you're adding and stuff like that. If you laid up the 148, which I think is what you get if you didn't round there or something like that, 147.5 or something like that, I'd probably take it. It'd probably be okay. Other questions on that? Okay. Now, when we talk about specific heat, and by the way, this is endothermic, so obviously we're transferring that heat to silver. So the silver is picking up the heat. So that's why we would expect our final temperature obviously to be higher as it picks up the heat. We can also use specific heat in a sort of simple process of, if we had some water, and let's just say we had about 125 grams of water in this example. Let's say initially our water here was at like 25 degrees Celsius. Obviously, we have the specific heat of water. And let's say we took a piece of metal here. And let's say we knew that the metal was like 95 grams, the mass of it. Let's say we heated that metal up to like 99 degrees Celsius. I'll go 0.0. And we want to know basically what is the specific heat capacity of the metal. So if I take this really hot piece of metal and then drop it, hopefully not from that distance, but I drop it from there into the water. When the hot piece of metal here, we'll make it red, goes into the water, the energy for the metal is going to be absorbed or released. It's going to be released, right? It's the hotter, right? So heat travels from hot to cold. So this metal here that just went in there is going to release all its energy basically to the water. And let's just say, for example, after that was done, the final temperature of the water ended at like 27.5 degrees Celsius. What's going to happen here is eventually that piece of metal will obviously come to rest at the same temperature as the water, right? So we actually will now know from this sort of experiment and measuring the water that the final temperature of the metal will also come to rest basically at 27.5 degrees. Now, we can use all the information we have for the water to help us figure out the specific heat capacity of the metal because we know a lot about the water. We can do the Q of the water here, which would be 125 grams our specific heat capacity there for water, liquid water, and our final temperature, which is 27.5 minus 25 degrees Celsius. And in this case here, we will get, we'll get approximately, it looks like, I think that's a 0.1307.5 joules. Again, at this point, if you wanted to, you could go to 2 sig figs based off of that. So approximately 1,300 joules of energy. 1,300 joules of energy was absorbed by the water, which makes sense. It is a positive value for Q, right? Which means it's absorbing energy from the metal. All of the energy that was gained by the water had to come from the metal that you dumped in there. So in this type of situation, we could say that Q of the metal would equal negative Q of the water. So it should be the exact same amount of energy that the metal lost, but it should be a different sign for the metal. And that would mean that the Q for the metal would actually be negative 1,300 joules. And that makes sense for the metal because it was hotter, it's giving off the energy. So it is a negative value. So now when we look at our metal over here and all the information from our metal, we now have everything that we need to go back into our specific heat equation and really solve for S here. And if we solve for S, it would be Q of the metal divided by M delta T. Putting in our numbers here, our Q of the metal again would be our negative 1,300 joules divided by the mass of the metal, which was 95 grams. And now our final temperature of the metal is actually less than our initial. So that's going to give us a negative as well, which is good. Because the negative we get here will cancel out the negative that we get there, and we will end up with a positive value for the specific heat capacity, which is what you want. So 1,300 divided by 95 divided by 27.5 minus 99. There. Gets us a specific heat capacity for this metal of 0.19. And the units here would not cancel, so it would be joules per gram per degree Celsius. So this is a very common process using specific heat and really using water and really the temperature change that occurs with water to figure out how much energy is being released or absorbed as a result of a reaction. You could do this very simply with 2 styrofoam cups, basically, and a lid, and you can do this and just a thermometer and figure out the temperature change that occurs with water. As well. This is also how they figure out things like calories in your food. They could burn it and follow the change in the temperature of water, and they can figure out how many calories the water gained from the burning of your food, which they can then translate into nutritional calories and tell you how many calories are in your food. They sometimes use what is referred to as a calorimeter for that, or a bomb calorimeter, which basically means they set the thing on fire to your chocolate chip cookie and let it burn. Yes. Did you say sad? It is sad. It is sad. We used to do experiments years ago. They make you bring like a Coke can. You could set like a Cheeto on fire underneath the Coke can. The can would have water in it, and then as it's burning, obviously you can follow the change in temperature of the water, and you can figure out how many calories were in like a Cheeto or something like that. Any questions on specific heat? Yeah. I did it because I don't know. I felt like sig figs today. I don't know why, but this is 3 sig figs. This was 4 sig figs. And when we subtracted this, we should go to the first decimal place, which gave us 2.5, which was 2 significant figures. So that's why I took this guy down to 2 sig figs here. And then when I divided here, it looked like I just went with 95 here. Again, this was 2, 2, and I think we actually got 3 on that one. So a 2 would be the end result there. Other questions? Yes, sir. You should follow the normal sort of significant figure rules we talked about previously as you go through these things and sort of round. Again, there's not probably multiple steps you're doing in these. So, at the end there, you just kind of clean it up, then maybe the right sig figs would be good. All right. So that was the example we did. Let's also talk a little bit about energy and phase changes. And like I said before, we use the specific heat capacity or specific heat equation there really to figure out the energy that occurs when we take a substance really from different temperatures, and we're not changing the phase of it. So it remains the same all the way through. So like our piece of silver there was the same solid all the way through. Our water was liquid all the way through that process. But there is a certain amount of energy required to do nothing more than take a substance from one phase to the next. And for example, when we go from solid to liquid, which is the process of melting or freezing, this occurs at the same temperature. And it requires a certain amount of energy just to do that. So for example, at 0 degrees Celsius for water, that is when that occurs. And at exactly 0 degrees Celsius, you actually have both phases in equilibrium with each other. So you got a little bit of ice, you got a little bit of liquid water. It's not until you get above 0 degrees Celsius that you really transition fully into liquid, not until a little bit below 0 degrees as you transition into ice. But at exactly 0 degrees Celsius, you basically have both phases happening. What determines which way you go is, do you continue to put energy in, you'll melt. And if you remove energy, you will freeze. The amount of energy to go from solid to liquid or liquid back to solid is what is referred to as the heat of fusion. It is sometimes referred to as the delta H of fusion. And for example, for water, it's roughly 335 joules per gram. And if you were going from solid to liquid, that's an endothermic process, which means it would be positive 335 joules per gram. And if you were going from liquid to solid, that's exothermic. It needs to be released. It would be negative 335 joules per gram. Again, same number, but just the sign is different depending on sort of which direction you are going. So, if I had a certain amount of ice, I could use the specific heat, the heat of fusion for water to figure out how much energy is required to do that change. So let's take a look at that. How much energy and calories are absorbed when 50 grams of ice cube is melting? So here they did give us the heat of fusion actually in calories. So if we were to do this, it's a simple, straightforward sort of calculation here. You would take the 50 grams of water, which is the ice. You would use the heat of fusion so that the grams cancel. So the 79.7 calories per gram, those guys would cancel, and we would get approximately here 50 times 79.7, 398.5 calories, which once again, like a 399 calories probably is where we should end up in this particular case. Any questions on that? And again, obviously, you could use my 335 or 333, depending on your book, joules per gram, and do basically the same calculation. So that much energy is required to do nothing more than take ice at 0 degrees Celsius to basically liquid water at 0 degrees Celsius. We're not changing the temperature, but we're just changing the phase. So there's a certain amount of energy just required to do that simple thing. If I then wanted to take my liquid water at 0 degrees to liquid water at 100 degrees, that would be liquid water and changing the temperature, which then you would go back to the specific heat equation that we just used there. So you can sometimes use these guys together, depending on sort of the problem. Any questions on that there? Go. There we go. There we go. Did I miss a 0 on that? I must have. Let me see. 50 times. I did. I'm sorry. I think I cut a 0 off there. Huh? Oh, because they use a different number there. I see. All right. So try that again. All right. 50 times 79.7. I guess it is 398. The decimal moved over. Sorry about that. I must have forgot to put the 0 there. So that would round there into 3990 calories. That would be good. Also good to punch it into the calculator correctly. I think that probably helps a little along the way. Okay. In addition to the phase transition that occurs at the normal melting point and freezing point, which is what we just looked at the normal boiling point is really where we get the transition between liquid to gas or gas to liquid at the normal boiling point is where that happens. Again, both of these processes do happen at the same temperature. So once again, for water, that's 100 degrees Celsius where that occurs. And exactly at 100 degrees Celsius, you once again have both phases in equilibrium with each other. Not until you get a little bit above 100 that you got your gas, not until you're a little below that you have your liquid. And there is, again, a certain amount of energy simply to do that transition, not change the temperature. And that is what is known as the heat of fusion, heat of vaporization. And again, sometimes referred to as the delta H of vaporization is how it's sometimes abbreviated. And for water, it is roughly about 20 to 60 joules per gram, the heat of vaporization. Does it take more energy to do the solid to liquid or the liquid to solid transition? So that is the heat of vaporization. It's about 335 joules per gram to do the heat of fusion, which is your solid to liquid. This one is obviously your liquid to gas and back. It takes a lot more energy, right, per gram to do that transition to go from liquid to gas. And that is because when you do that transition at that point, everybody needs to completely kind of break apart from each other. So it takes a lot more energy to break everybody apart. When you do the solid to liquid transition, everybody's still relatively close to each other, a little bit more room for movement. But definitely when you transition into the gas, it takes more energy to break everybody apart. So always a lot more energy to do that transition than the solid to liquid transition. Any questions on that there? We also could do that for sublimation and deposition. Sublimation, once again, is going from solid to gas, skipping the liquid phase. And deposition is going from gas back to solid, and also, again, going from solid to gas is endothermic. Energy has to be put in. Going the opposite way is exothermic. So a reminder that as you are going in this direction in terms of phases, that is all endothermic. You got to throw energy in there, do that. And obviously rolling the opposite way from gas to liquid to solid, that is all exothermic processes where you have to release the energy to do that. When you release the energy to do that, people flying around lose the ability to fly around. They kind of clump together, and you continue to release the energy. They clump together into the solid phase as well. Any questions on any of that there? Now here's just a table summarizing the processes that go from different phases as we talked about. This is a heating and cooling curve. So if this was, say, water, this would be right here at 0 degrees Celsius. And if this was the boiling point for water, this would be 100 degrees Celsius. So anywhere where you see the line sort of plateau out, like here, that is your heat of fusion in this case, going from solid to liquid. And up here would be your heat of vaporization, going that way. So if you had to do a calculation going from those points, this is where you would use your delta H of fusion. This is where you would use your delta H of vaporization up here. Anywhere on this graph where you kind of go sort of upwards and not plateaued out, like this way, or this way. All those green ones are places where we change the temperature, but the phases stay the same. So this is all up on top there, gas. In the middle is all liquid in that area. And this is all solid in that area. And we're just changing the temperature. If you had to figure out how much energy was required for those spots, those all are where you would use your specific heat equation to do that. And if you wanted the total amount of energy to do the whole process, you could add up each step. So it all kind of occurs at one step. So let's just say, for example, we took 125 grams of ice at 0 degrees Celsius, and we wanted to take it to up here, which would be 100 grams of steam at 100 degrees Celsius. So the very first thing that would happen in this process is we would need to take the ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. And that is basically coming from here across here. That would be like step number 1 right there. And that is obviously, we're not changing the temperature, but we are changing the phase. So that would be our heat of fusion. So we could do our calculation of 125 grams, use the heat of fusion for water, and I'll just use the number I wrote up there earlier, 335 joules per gram. And if we do that here, we get 41875 joules. So this is the energy required to take us from basically here to here. At this point, what we are doing is we are sitting at 0 degrees Celsius liquid water. The next process would be going from there all the way up to 100 degrees liquid water. And that would be the second step. And that would be the same phase, but different temperatures. So we would use our specific heat equation, and that would be 125 grams, our specific heat capacity for liquid water, and our final temperature 100 minus 0 degrees Celsius here. And the amount of energy required to do that change there would be 125 times 4.184 times 100, roughly 52,300 joules at this point. Now, you may say to yourself, I'm at 100 degrees Celsius, but I am at 100 degrees Celsius liquid water. So the last step would be to take it from 100 degrees liquid water to 100 degrees steam, which would be the third step that you would have to do in this process. And that would be the heat of vaporization that you would need. So the third step here would be to go from 100 degrees liquid water to 100 degrees gas, basically. So we'll use our 125 grams, our heat of vaporization, 2260 joules per gram. And we will end up with 282,500 joules. At this point, the total energy would be found by adding all the steps together. The energy required to do each of those steps we would add together. So we would add step 1 to step 2 to step 3, all the energy values, And if we did that, we would end up with roughly here, we'll call it 376,675 joules, or approximately, we'll round it a little bit to 377 kilojoules of energy is needed to do that entire process, to go from 0 degrees ice to 100 degrees steam, basically. Any questions on any of those steps? So again, if you have to do some type of phase change along the way, should occur at the same temperature, and that means you should use a fusion or a vaporization depending on which phase you're changing. If you're doing anywhere where you are in the same phase but change the temperature, you should use the specific heat equation. And one last point is, as we can see here in the calculation, it clearly takes a lot more energy to do that last transition, going from liquid to gas, 282,000 versus about 41,000 joules of energy to just do the solid to liquid transition. So again, a lot more energy required to do that transition. Any questions on any of that? What would be the only difference if I started at 100 degrees steam and went down to 0 degrees ice? What would change? If I went backwards, started with steam and removed all the energy to get the ice. Yeah, it would be exothermic, which means all these values here would be exactly the same, except that they would all be negative, right? So our first step would be negative 335, which would give you a negative number. Our second step, instead of going from 100 to 0, we would be going from 0 to 100, which would give us a negative. And our last step there, the 2260, would be negative. So you would end up with the exact same number, except that it should be negative because it's exothermic and the energy is being released as you do that. Any questions on specific heat, phase changes? Okay. This is the same curve except cooling, going in the opposite direction there. And I believe that should be this chapter here. It is. That's good. All right. Any questions on that chapter there? All right, we're going to roll into chapter 8 here. Okay, so next up is chapter 8 here, which is solutions and some other information, I think. All right, so let's talk about it. So first off, we're going to talk a little bit about mixtures and some pure substances. A reminder that a pure substance is basically any covalent compound or ionic compound that is basically by itself. So if you have something like water, obviously that is a pure substance. When we put two or more pure substances together, that is when we do get mixtures, right? And if we took water plus something like sodium chloride and put them together, we would get basically a sodium chloride solution, which is actually a mixture. And there's two types of mixtures. One is a heterogeneous mixture, which is not uniform. You do see different layers. So even after sufficient mixing, everything you can still kind of see everything in there. And a solution, which is sort of the topic of this chapter, which is a homogeneous mixture. So it looks the same throughout. Everything sort of dissolves in it and you just see something. So again, if you had something like salt water and you just looked at it, obviously it just looks like water. You can't really see the salt in it because it's dissolved, but it is still there. A reminder that these guys are physical changes. Yeah. Because obviously you could heat up the salt water and evaporate off the water and be left with obviously just the salt part there. Now, when we talk about solutions really are homogeneous mixtures, and solutions really contain are made up of two different things. One is the solute. The solute is the smaller substance, and one is the solvent, which is the larger substance. So in my example I just did there, where we take the water plus some solid sodium chloride, The water here is our solvent. The sodium chlorides are solute. And once again, when they dissolve in each other and make that mixture, we actually do get a solution that is the sodium chloride solution. And solutions typically symbol next to it, that AQ symbol, is typically what our solutions will get. How do you know what the solute is for a solution? It's a pretty simple answer. It is the name of the solution. So a sodium chloride solution, sodium chloride would be the solute. If you had a potassium bromide solution, potassium bromide would be the solute. So whatever the kind of name of the solution is really the solute. A reminder as well, and I think we might have talked about it, but just in case, there is a difference between aqueous and liquid. Again, a liquid is really something that is a pure substance, like water by itself would get the liquid denotion, and something that is aqueous basically means you took something and you dissolved it like we did here. Is water always the solvent? The answer is no, but water is a very common solvent for a lot of things because, as we just talked about, it has the ability to hydrogen bond, which means it works really well with ionic guys, doing, I think we talked about it as well, sort of an ion dipole interaction where the water is able to surround the ions when they go into solution, and it works really well. Again, water would be a really bad solvent for something that is nonpolar, so it wouldn't work very well. They would just separate out from each other. So let's talk a little bit about some other concepts of solutions, for example, colloids and suspensions. A colloid is a homogeneous mixture with really larger sort of particles. These are particles in a colloid, cannot be filtered from other components. They do not settle out, so they're relatively large and you can't kind of get them out by filtering them. A suspension is a heterogeneous sort of mixture, which means you do see the different parts in it. And they're really so large that you can really just kind of see them with your naked eye. They don't dissolve. They also, they can be filtered away from the liquid and separated by centrifuging. Centrifuging is basically when you have like a mixture and a liquid, some solid in there, spins around really, really fast. And basically all the solid ends up on the bottom and you have sort of the liquid up on top. So colloids, things like proteins and stuff like that, suspensions, you know, you could, like we have water and you threw some sand in there, that's a suspension. The sand, you can see it, it's big enough. You could filter out the sand right from the water. If you roll it through a funnel with some filter paper, the sand will get caught on the filter paper, water will go through the funnel and stuff like that. So a solution is really small in size. Colloids, like I said, are really larger, and suspensions are even larger as well. The only one that really does sort of settle out are suspensions. The other ones do not. So let's talk a little bit also about electrolytes and non-electrolytes. An electrolyte is really a substance that when it goes for a swim, it basically will break apart into ions. And when it breaks apart into ions, it's able to sort of conduct electricity because of the presence of those ions. So sodium chloride in water basically is a very good electrolyte. It will break apart into 100% sodium ions and chloride ions. And because there's a lot of ions floating around that solution, it will conduct electricity really well. Sometimes people do an experiment where they take some electrodes that's hooked up to a light bulb and they kind of put the electrodes in the solution. And in the case of something that is a strong electrolyte, it will 100% break apart into ions. And because there are so many ions in that solution, in the light bulb example, it will shine very brightly. So the light bulb will be very, very bright. It will conduct electricity really, really well. There are electrolytes that are weak electrolytes. And unlike strong electrolytes, weak electrolytes will mainly stay together. But they will break apart a little bit. So something like hydrofluoric acid is actually a weak acid, also a weak electrolyte. When it goes for a swim, it will break apart into H plus and F minus. So it will produce a little of these ions, which means it can still conduct electricity, but it will not conduct electricity anywhere near as good as a strong electrolyte like sodium chloride or hydrochloric acid, which is a strong acid. But it will mainly stay together. So it will mainly be this guy here that is in solution. So in that solution, you will, if you looked at it, would mainly have HF floating around and a little bit of H plus and F minus, but a majority of what's in that solution is still the whole thing together. The way you can recognize, say, a weak electrolyte versus a strong electrolyte when you look at the equation is by the arrows that you see. In a strong electrolyte, you will have basically a one-way arrow. In a weak electrolyte, you will have arrows that head in both directions, and that is basically how you know that. So if you had something like hydrochloric acid, which is a strong acid and a strong electrolyte, hydrochloric acid would 100% break apart into H plus and Cl minus. So in that solution, that's pretty much all you have in there is these guys, is those ions. So it conducts electricity really, really well. Again, if you did sort of the light bulb example on the weak electrolyte, the light bulb would go off, would go on, I guess is the way you say that. It would turn on, but it would be very, very dim. So it would still has the ability to conduct electricity, but it would be very, very dim versus a strong electrolyte. Any questions on that there? A non-electrolyte, on the other hand, is something that will dissolve in water and will mix with water, for example, but it will not produce any ions. So, for example, sugar. If you take some sugar, right, you put it in water, it will dissolve. Sugar is made up of carbons, hydrogens, and oxygens, which means those guys are covalently bonded together. They're not going to produce any ions in that case. They're all nonmetals. So even though something like sugar will dissolve, it will not produce any ions. And because it doesn't produce any ions, it will not conduct electricity. So if you did like the light bulb example and stuck it in a non-electrolyte, your light bulb would not go on at all. So strong electrolyte, lots of ions in the solution, conducts electricity really well because of those ions. Light bulb goes off very bright. Weak electrolyte, little bit of ions in the solution, still able to conduct electricity. So kind of light bulb goes off dimly and conduct electricity that way. Non-electrolyte, no ions in solution, does not conduct electricity pretty much at all. Is pure water a good electrolyte, a good conductor of electricity? Pure water? Pure water is a bad conductor of electricity because it's H2O, it's all nonmetals and covalently bonded. Just so we're clear, the water that comes out of your pipes at your home is not pure water. So you will electrocute yourself if you decide to blow dry your hair in the shower, because it will actually electrocute you. That's because they clean water by actually putting a lot of ions in the water to clean it. So there's a lot of ions, in sort of the water that comes out of the tap. Take home messages: do not blow dry your hair in the shower, right? So as I mentioned before, a strong electrolyte will 100% break apart and form those ions. A weak electrolyte will only partially break apart, but they both can conduct electricity. Obviously, a strong electrolyte conducts it much, much more, and obviously a non-electrolyte does not. So down here, some examples of some strong electrolytes. Strong acids and strong bases are also strong electrolytes. Any ionic compound that pretty much will go for a swim will be a strong electrolyte. A lot of weak acids and weak bases are weak electrolytes, like ammonia, that's acetic acid and hydrofluoric acid. And then non-electrolytes are some of these guys, and also like sugar is a common one as well. So let's talk a little bit about equivalence and non-electrolytes here. So equivalence is sometimes a unit of measurement for solutions that are used to help us measure sort of the amount of ions that are floating around in that solution. The equivalence is really a lot of times used as like a conversion factor to convert into a particular type of unit for a solution. The way we could figure out the number of the way we can figure out the number of equivalents is based on the charge. And it's not based on whether or not it's positive or negative. In this particular instance, it's just based on the actual number. So if you had a sodium ion, sodium has a +1 charge or a 1 for the charge, you could come up with really a conversion factor that says for every 1 mole of sodium ions, I have 1 equivalent. We could do that for any type of ion, a positive or negative. So if I had sulfate, which is SO4 2-, the charge on the sulfate is -2. And again, the minus doesn't matter here. It's actually the 2. And we could say for every 1 mole of sulfate, I would have 2 equivalents, which again is equal to the charge on the ion. Again, if you had phosphate, PO4 3-, 1 mole of phosphate would give us 3 equivalents. So when we have an ionic compound, as we've talked about, we basically always want to put it together in a way in which all the charges basically cancel each other out and we get a 0 overall charge. And we could represent this or see this by calculating sometimes what is referred to as the equivalence per liter for each of the ions that are in a solution. And because everything balances out correctly, if you do it right, you actually will end up with the same sort of charge that's floating around in a solution. So if we went through sort of a calculation like that, actually we'll do it here, I think, maybe. So let's just say, for example, we had a solution that was 1.25 moles per liter. Actually, let's do a smaller number. Actually, let's just do, sorry, let's do 0.25 moles per liter sodium sulfate. Right now, when we have sodium sulfate in a solution, it is not going to stay together, right? It is actually going to break apart into the 2 ions that make it up, 2 sodiums and 1 sulfate, basically. And in solution, we would have 100% of these guys basically floating around. Now, if we took sodium, as we just did a second ago, we saw that for every 1 mole of sodium ion, there was 1 equivalent. And we saw also a second ago for every 1 mole of sulfate, there is 2 equivalents. So what I want to figure out is the equivalence per liter for both sodium and the equivalence per liter for sulfate in this solution. So we're going to do a little bit of conversions here to get us there. We're going to start with the sodium. So starting with the 0.25 moles per liter of the entire thing. We could do a mole to mole relationship here for every 1 mole of the whole thing. I get how many moles of sodium? 2, just like in stoichiometry. So a 1 to 2 relationship. So if I do 1 mole of the whole thing, I get 1 mole of the sodium ion. If I stop right there, the moles of the whole thing will cancel out. And what I'm left with up on top are moles of sodium over liters. And that's close to what I want, but I want equivalents per liter, right? So I could do one more conversion here using our equivalents per liter, our equivalents per mole. And for every 1 mole of sodium ions, there is one equivalence of sodium. This will cancel us out. I'm sorry, I just should be a 2, right? There it is. Sorry about that. That should be a 2. There. That's because that's a 2. That will cancel our moles out. And now I got the right number in there. We would end up with 0.250 times 2. And that would give us 0.5 equivalents per liter of sodium ions that are floating around in that solution. So that's basically like the concentration of the sodium ions, the positive guys that are basically floating around in that solution. And again, the 2 came from the 1 to 2 relationship there. Any question on that calculation there? We're going to do the exact same calculation for the sulfate. So we'll start with the whole thing once again. Moles per liter of the whole thing. When we look at the whole thing to the sulfate, now I'm going to do it right here, that is a 1-to-1 relationship. So 1 mole of the whole entire thing gives us 1 mole of sulfate. These guys cancel. And now I have moles of sulfate on top per liter. Now I could use the moles, the equivalents here. And for 1 mole of sulfate, there are 2 equivalents. So the moles of sulfate cancel, and I end up with 0.5 equivalents per liter of sulfate in that solution. So the message here is we see that we actually have the exact same concentration based on charge of those ions floating around in the solution. And that's why everything is balanced, right? When we put it together, we need 2 sodiums for every 1 sulfate to balance out the negative charge. So in terms of sort of the charge concentration that's floating around that solution, we have an equal amount of positive charge to negative charge. And that's basically always what you get in an ionic compound. And that's really the purpose of why we, balance out the charge when we put it together to write a formula for an ionic compound to balance out the positive and negative charge. So that when you make a solution like this, for example, you have the same concentration of positive charge floating around as you do negative charge. Any questions on any of that there? Okay, we will lay it up there for today.